Okay, in this section of chapter 10 that we're going to cover, we're going to look at changes that happen to the nucleus of an unstable atom. Let's remember a little bit about atomic structure. Protons and neutrons are both packed into the nucleus. Protons have a positive charge and neutrons have no charges. Let's think about what we know about charged particles. Like charges are going to repel each other and opposite charges are going to attract each other. So the protons will repel or push against other protons. Why doesn't the nucleus then fall apart? Well, the strong nuclear force is going to act against those repulsive forces and hold the neutrons and protons together in the nucleus. This is a much stronger force than the electrostatic force that causes the protons to repel one another. In stable nuclei, the attractive forces have to be stronger than the repulsive forces to keep the nucleus stable and intact. This isn't always the case, and some nuclei are unstable and they will emit nuclear radiation and they will break apart and decay. So, what causes a nucleus to decay? Again, it is an unstable nucleus due to an imbalance between the protons and the neutrons, and the repulsive forces then would be stronger than the attractive forces. Nuclei with too many or too few neutrons are going to be unstable and will undergo decay. So it's an imbalance between the protons and the neutrons. Again, remember those protons have a tendency to push against each other, and the neutrons are going to act to buffer or support that and keep the nucleus and act like the glue. That strong nuclear force will act like the glue that holds the nucleus together. Really large nuclei are going to have a larger imbalance between their protons and neutrons. So nuclei with more than 83 protons will always be radioactive. They will be unstable, no matter how many neutrons. These nuclei will decay into more stable isotopes and emit energy and nuclear radiation as they decay. There are a handful of different nuclear reaction types, four main types. In this course in Honors Physical Science, we will understand fission and fusion so that we can then discuss stars. In chemistry, we'll go through the other types of nuclear decay. So fission is the splitting of a larger unstable nuclei into a smaller, more stable nuclei. Fusion is the combining of smaller nuclei into larger nuclei. All of these processes, or both of those processes, release a large amount of energy. Nuclear decay is a process by which an unstable isotope will spontaneously transform into a new element by emission of ionizing radiation. So it'll break down and change and it'll release energy and decay particles. And spontaneously means it needs no extra energy to make this happen. It will happen naturally. It does happen at different rates, and depending on those rates depends on how these different nuclear isotopes, radioisotopes, are used. Transmutation is a non-spontaneous process. This involves neutron bombardment. So we have to take a neutron and fire it at a stable nucleus, which will cause that nucleus to become unstable and then undergo decay. Equations, whether it be chemical equations or nuclear equations, are always going to give us information about the reaction. In a balanced nuclear equation, it will indicate a rearrangement of the subatomic particles that are happening during a nuclear reaction. It will follow conservation laws and show that matter has not been created or destroyed, and will be balanced in two ways. The sum of the mass numbers of the reactants, those are the starting substances in the reaction, will equal the sum of the mass numbers of the products. Those are the new decay products that are formed. They will be visible on the right side of the reaction arrow. Remember, the mass numbers are written in the upper left-hand corner of the nuclear notation. We must also balance the sum of the charges of the reactants, and that must equal the charges of the products. You will see the charges written in the lower left side of the nuclear notation. In this case, we'll be focused on the protons because the protons are the charged particles in the nucleus. So we're looking at the atomic number in the nuclear notation. So we'll balance the mass number and balance the atomic number. And we'll need to make sure that those numbers are the same on the left side of our equation as they are on the right side of our equation. Here's an example of a balanced nuclear equation. We can see that this starts with an isotope of uranium-238. So there's the U for uranium. The 238 in blue up top is the mass number, and the 92 is the atomic number. Then you can see the reaction arrow showing that uranium is decaying, and the products of the decay are thorium-234 and helium-4. You can see as uranium breaks apart into those two pieces that the mass of the uranium-238 has decreased by 4, representing that helium nucleus that is broken off of the uranium atom. We can see that the mass number of 238 on the left is equal to the sum of the mass numbers of 234 plus 4 on the right. We can see that the charges, 92 protons on the left, the atomic number, is equal to the sum of the 90 protons in thorium plus the 2 protons in helium. So the mass number is conserved and the atomic number is conserved. There's also 2 examples in the bottom that relate to fusion and fission. So we can see that the mass of helium-4 plus the mass of lithium-6 is equal to the mass of boron-10, and that the atomic numbers of 2 plus 3 equal the atomic number of 5. That's the fusion example. And it's also the same in the fission example. Note in the fission example, there's a notation of 1 over 0 n. That is the notation for a neutron. And this is an example of a neutron bombardment. So that neutron is added to the uranium-235 nucleus on the reactant side, which causes it to be unstable. And then you can see the products of that decay on the right side. Pause the video if you need to examine these equations anymore. As you can see in those nuclear equations, it's important that we understand the notations for the particles. Remember, in our nuclear notation, the mass number is written in the upper left corner, the atomic number in the lower left corner, and then the element symbol. You'll notice that we're not dealing with ions because we're focused on changes only to the nucleus. In the hyphen notation, the element symbol is followed by the mass number. There's a few different particles that are important as we examine changes to the nucleus. The proton and the top left, the protons have a mass of 1 AMU and a charge of +1, and the symbol for a proton is a P. Neutrons have a mass of 1 and no charge, 1 over 0, the symbol of N. Electrons have no mass, 0, but a charge of -1 and an E. And I know my head is in the way of the positron, but the positron is the opposite of an electron. It has a mass of 0, but a +1 charge, and then the symbol of a P. Okay, I turned off my face so that you could see this better, and I said a P for a positron, and I meant an E. So fix that in your notes. Here we go, moving on. We're going to talk about fission. So fission, remember, is the process of splitting a large atom with a heavy nuclei into atoms with a lighter nuclei. Both neutrons and a large amount of energy are released during a fission process. For example, fission releases more energy than chemical reactions like the combustion of dynamite, TNT. Oftentimes, fission starts with a more stable nuclei. In order to make that nucleus unstable, it will involve neutron bombardment. Bombardment means to hit, high speed, lots of force and energy. So a neutron is fired at a stable nucleus. So a neutron will collide with this nucleus of a stable atom and cause that nucleus to become unstable and break apart. So here's our example of a nuclear equation for fission of uranium-235. You can see that the uranium-235 on the left is one of our parent nucleus. You can see that a neutron was added to it. So that's the representation for neutron bombardment. We are adding a neutron to the nucleus of a uranium-235 atom. That will cause it to break down. It's going to break apart into barium-140 and krypton-93. It will release energy, and it also will release 3 neutrons. These smaller nuclei of barium and krypton don't need as many neutrons to keep their nucleus together, so those extra neutrons get released or emitted as part of this fission reaction. So because of those extra neutrons that will also be available to then collide with more uranium-235, what happens in fission is a nuclear chain reaction. This would be a continuous series of nuclear fission reactions where one reaction is going to trigger another reaction. A smaller nuclei is a product of the fission reaction. And again, like I said before, those smaller daughter nuclei will need fewer neutrons to be held together, so they in turn release those extra neutrons. Those extra neutrons will then be available in that sample of an element to collide with more of the parent nuclide. So you can see in the example on the right that we have a uranium-235 that's hit with a neutron. It breaks apart, it releases 3 neutrons. Those neutrons collide with 3 new uranium-235 atoms. Those break apart, and 3 more neutrons are produced from each of those decay products. And those in turn will hit more uranium. So we can see that new uranium-235 chain reaction. This is important because this is applied in nuclear power plants. So energy produced in nuclear chain reactions can be used to generate electricity. What's really important is to understand the term critical mass. So this is the smallest amount of that fissile substance, so of that uranium or plutonium, so of that radioactive isotope that's going to be used, that is going to provide enough neutrons to start this chain reaction. If the amount of a substance is less than the critical mass, a chain reaction will not continue. Important that in a nuclear power plant, control rods are used to maintain the rate of this reaction so it doesn't get out of control and become unsafe. So these control rods will absorb some of the neutrons that are released, and that will slow the reaction down. This reaction, again, produces a lot of heat or energy, and that heat obtained from the fission reactions is going to heat up water, turn that water into steam. The steam will turn the turbine that's connected to a generator, and we get an output of electricity. Here's a picture of a nuclear power plant again, number 1. So we have a fissile material, uranium-235, in a fuel rod. So again, just where they're storing the uranium-235. It's going to start a chain reaction. The control rods also in there are going to, again, maintain that speed of the chain reaction by absorbing the extra neutrons to slow that reaction down. And then we have a coolant, usually water, absorbs the energy from the chain reactions. It changes that water to steam. The steam turns a turbine, which is attached to a generator, and the generator is going to take that energy, mechanical energy, kinetic energy of the spinning turbine, and turn it into electrical energy. There are advantages and disadvantages of nuclear power plants in using fission. Energy produced from nuclear fission is used to provide electrical energy to millions of homes and businesses. It's not as popular in the US as it is in other places. Another advantage is that it does not produce gases like greenhouse gases that pollute the air from the burning of fuels, fossil fuels. There is more energy in known uranium reserves than in the gas and oil reserves. However, there are some disadvantages to it. Radioactive products of fission could escape into the environment and spread dangerous nuclear radiation. Because of that, nuclear reactors need many safety features, which can make power plants very expensive to build and maintain. Another cost is the storage of nuclear waste. So the byproduct of these fission reactions can still be radioactive and must be stored safely for a long time, thousands of years, until other decay processes have happened and they have formed less harmful, more stable, and non-radioactive elements. So storage is very important. This is also applied in the use of nuclear weapons, so this chain reaction principle. And in nuclear bomb, we have chemical reactions that trigger the nuclear reaction. So we have uranium-235 or another fissile isotope like plutonium. It's packed into a container surrounded by an explosive material. So in the chemical reaction, the combustion of these explosive materials, that is going to trigger those uranium atoms to exceed the critical mass and would start a nuclear reaction. And again, in a nuclear bomb, during a nuclear weapon, there aren't control rods. So all of those neutrons get released and the reaction is quite large. We're also going to discuss nuclear fusion. Nuclear fusion is the opposite of fission. In nuclear fusion, light atomic nuclei are going to combine, join together, and form heavier nuclei. This takes place in the sun and other stars, where huge amounts of energy are produced when hydrogen nuclei fuse to form helium. It takes a lot of energy to start a fusion reaction in order to take those nuclei and push them close enough together so that the strong nuclear force can overcome those repulsive electric forces. Where is that large amount of energy come from? In stars, there's extremely high temperatures and pressure provide the energy to bring hydrogen nuclei together. Scientists are actively looking for ways to use fusion as an alternative energy source here. However, it has been difficult to produce those conditions in a laboratory. It's very desirable as these reactions release very little waste or pollution. And here are a couple pictures of fusion reactions. You can see on the upper right-hand corner, the D in the upper left side and the T are representing two isotopes of hydrogen. So you can see hydrogen with a mass of 2 and hydrogen with a mass of 3, and they're pushed together, and the center is representing taking place in the sun. And then the byproducts on the right side are helium, lots of energy, and then excess neutrons. In our next unit, we'll discuss some of the processes of fusion and the life cycle of a star.